So hello everybody and welcome to another session. This time to the DBSCAN. I opened here Google Colab because there are some packages to install for this session in order to draw the map, which I don't forcibly want to install on this little machine. The files that you need for this course, basically you can get them here. So you need basically this file here, which is part of the dataset, and another part of the dataset which is kind of the weather data. You can download it here, so just use these two URLs. You can pause the video to type them or to copy them. I will put them also in the video's description, so that you can easily download the datasets needed for this session, for this clustering session, and to play around with this and to see a bit about the cool stuff that you can do with it. Okay. So fine, so good. I will just check if I have these two files already here. I have them downloaded, that's so fine. I will upload them here to Google Colab so that you also can see how you can use Google Colab for these sessions that I've made before if you don't want to install an IPython notebook environment. So just I can go here to files. It starts to connect to a runtime here, and here is a file upload button. So I just use this file upload button, I select my two files, and in a short moment basically we will have these two files uploaded. Yeah, it takes a bit time. The internet connection here in Beirut is not the best, but it works. That's basically the story. So it will upload basically these two files here into my runtime. So fine, so good. As it does this, we can start basically to write some little code. So we see here we have a CSV file, we have a pickle file. As I uploaded them, they're kind of in the working directory of this notebook here. And this, you can also of course do this in your own environment at home. For me it's just here more convenient to use this Colab environment, and in order not to install certain libraries, you can do this in any environment that you like. Okay, so I uploaded the files. How can I work with a pickle file? Basically we have this pickle library. What is a pickle? Just a quick excursion. This might also be interesting for the others here, for all for your Python context in general. So let's import the pickle library, and the pickle library basically allows you to store Python objects just into files. So just imagine you have a list, you want to store this list into a file. You can just use the pickle library to do this. This is basically what I've done here. I stored some weather data and I dumped it in this pickle file that you can use in order to load the data. Yeah. Okay. So we'll use the pickle library to load here. It's very easy. So we have basically, I will call this here, as this is about France, I will just call this here météo. So météo basically in French means the weather. For you can call it weather in your case. Just for me it's a bit more convenient to call it météo in this case here. And we call it pickle load, the pickle load function, in order to load this pickle file that we've talked about before. And what do we need? A file object. So first I have to define my file. So how do I do this? We already know this. So file, basically we open the file, and here we open the pickle file. What was its name? Weather for wheels. So weather for wheels with underscore, as I named this here, and the pickle file. Okay. And here I say, which is new maybe for you, is we don't just put an R, but we want to have a binary file. So we want to read this as a binary file, open it as read binary. Okay, and then I can use this pickle load functionality here and say F, just the file that I have here. And of course, then we don't need the file anymore, so we can close the file and we can basically read this data here. Okay. So this is how you use pickle files. If you want to store something to a pickle file, you can use this. I make just a quick excursion about here. You can use this in the same way. So I could use fopen something like my pickle. In this case, you use write binary, and then you have a pickle dump function. Hopefully we get what it does. So object, you put the object and the file that you want to have. So basically the object, so basically if this is a list, yeah, you can use here my list f, and then you close the file, and you can then of course load it just with the way you reload this file here, yeah. Quick excursion to pickle objects. Okay, this is not needed, so I will just delete this here again and go back to our pickle file. We load the pickle file into our notebook environment here. If I type right now Meteo, we see here I have responses. So the way this was done, basically this was downloaded from a weather service. This is JSON encoded. So if I do here, basically these are all responses. So if I just go to the first one, what does this look like? And it says response to 100. This doesn't help us a lot, but basically we can do here, you can type here JSON and do something like this, and then we get our JSON file out, and this looks like basically like a dictionary, and it works in Python also like a dictionary, as you have seen the dictionaries, how they work together. Okay, what do we have here? So each index here basically gives you a town, okay, and the .json basically gives you information about this town. And we have here what we want to have is basically the temperature, the wind speed, things like this, the pressure, the humidity, some kind of this data out of here, and we will access this and work together with our use this then in our DBSCAN that we have seen basically in our last lecture, in order to work with this. Yeah, as you have seen, this comes from weatherstack.com. For those who are interested how this works, there is basically a requests API in Python, so you can use requests, and with these requests you can access basically REST APIs, so RESTful state APIs over HTTP, and get data like this from them back basically. Yeah, this is how this works. The requests library is built for this. In the old days this service was free. This service, sadly, basically this weatherstack.com, they closed their service, so you will get data from 2020 when I downloaded this the last time for the French towns, and we will play basically with the French weather a bit and with DBSCAN in order to get you an introduction how to perform clustering and how to use the DBSCAN algorithm and how clustering with the scikit-learn library works. Okay, so fine, so good, enough talking. We also have this second file basically which gives us the towns. So I used this file basically to get an index of all the towns, and from these towns basically I downloaded then the weather data. Yeah. So this is a CSV file that I got from INSEE. INSEE is a French institution for statistics. They provide files like this. This is a pretty old file. I took here basically all towns in France that have more than 10,000 inhabitants, yeah, which population is bigger than 10,000. And this is basically, I stored this in this real CSV file that I've shown you where you can download it. Yeah. So I read this with this read CSV story. I also import at the same time the pandas library, as this is pretty handy. And if then I go into wheels and I show this quickly, we see here that we have basically the name of the town, the population of the town. So as I said, I took all towns that have more than 10,000 inhabitants. If we see this, these are 889 towns. This is enough for our clustering data set. Here you have the name of the town, and what is very important, we need this longitude, latitude story here, latitude, longitude, in order to locate the town on a map, and we will play around with this in order to see some fancy things that you can do with, as I said, with clustering algorithms and how to cluster data. Okay, so fine, so good. We have our towns, we have our weather. What we want to have is basically one data frame where we have the weather and the town. I mean, here we kind of have this in this JSON file that we got back from our service, but we want basically to extend, so also to play around a bit with the pandas library, to extend this this data frame into something that we can use for our clustering story. Okay, so how do we do this? Basically, we want to extract the wind, the temperature, the humidity, and the pressure from this dictionary, from this JSON story here above, and create this in the right way. So if I made this already right, so in this pickle, basically you find in the same lengths, because this was downloaded with at that time from this CSV file. So for each town, basically we have a JSON file in the same index as it is basically here in this data frame. Yeah. Okay, so how can we do this? You just basically need a list, with the list, then you can build a dictionary, and from this dictionary you can build a data frame. So let's create our lists. So let's create an empty list for temperature, wind, humidity, and pressure, and get basically some weather data out, and then we will cluster by this weather data and see if we kind of can see climate zones according to this DBSCAN algorithm that we have talked about in the last lecture. So for I in range, and we have here basically length, meteo. Okay, so how many weather data do we have? This is also, I could have done here fields. Yeah, so this is basically 889. Very easy, everything's easy and fancy. So we want to have basically for each one we want to append, and we want to append, you can try this out, meteo. Basically, as I said, this is a list of this JSON file, so a list of dictionaries basically. So this is basically the index here, and each index allows you to give you this dictionary back. Yeah. So how do we do this? So we need basically because for range I, then we want to convert this to this JSON format here, and then from this JSON format, as this works like a dictionary, we can dive into this. So we go here to current, okay, and this is kind of this current is kind of this sub-dictionary here, and in this sub-dictionary we get all our stories here out. So from this sub-dictionary we can then basically take, let's look it up again. So temperature, here is this here temperature, so you see current, this sub-dictionary temperature, we have wind speed, pressure, humidity. These are the things that we want to have here, no? Okay, we go back here, we have our JSON, we don't want to close this here, we have here basically what we want is temperature. Okay, so fine, so good, and we append this to our temperature story. Okay, very easy. We do the same thing for the other three in the same way. I will copy paste this to speed this up a bit. I will just copy this part here, and then we have, what was it called, wind speed, as we looked it up just before, no? Humidity, append, same story here, we paste this here in. The story is called humidity, we looked it up before, and the same thing for the pressure, no? Okay, so fine, so good. Pressure has arrived. Okay, very nice, and we have this basically in this story here. We have our lists. If right now, for instance, I type temperature, I have the temperature in all these places here. It's almost everywhere, as I see 11 degrees, or maybe a bit colder, sometimes even 15 degrees. We see here the list of temperatures for the town. If I go to the length of the temperature, we have 889, this is what we want. So for all of these lists we basically have this. As this is 889, this corresponds to my towns. as I told you, I downloaded this for each town with this requests API, and you can basically use this using this pickle here in the same way. And we want to have these lists. How do I append basically a list and make a new column to the data frame? This is very easy. You just basically type your data frame and you give a name for a new column, temperature, and you can say here, okay, this should be the list temp that we have created up here. Okay, I will not just do this for one column, I will do this for all the columns at the same time to speed this up here a bit. Here we have the wind, the humidity, I will just call this hum. Okay, and then we have here again the pressure and the pressure, and I have this kind of key, weather data for each French town, basically, which has more than 10,000 inhabitants in my data set. Okay, so let's do this here, let's execute this here. Add this to our video data frame. If I look at this data frame again, we see our data frame has been extended and we have right now temperature, wind, humidity and pressure. Okay, very nice, and we have the latitude and longitude, everything that we need in one data frame. This is what we want. Okay, so fine, so good. Looks very nice. Let's start what we can do with this. And in order for what we want to do, basically we want to see basically these towns on a map. This is why we have this latitude and longitude, and in order to visualize them we need a base map utility, and in order to use this base map utility we need to install some libraries. Okay, in this Google Colab runs like some kind of Debian based distribution. So in a Debian based distribution you can use the apt-get functionality. Basically you can install basemap is the Python library. You can look it up what kind of dependencies it has and install this on your own Unix distribution or in Windows in your IPython notebook environment in any way you want. Here I will just use basically apt install. There are some libraries that I have to install in order to make this happen, and they are called basically proj-bin. So this is kind of projection files that we need. So in order to use these latitude longitude values on a map, to put them on a 2D map, of course, and visualize them. So this is just installing some libraries. If you're familiar with a Debian based distribution, you probably know this apt command in order to install Debian packages also in Ubuntu or similar distributions that are originally based on the Debian distributions. They use this apt functionality in order to install things. So we install these libraries here. This way you can install these libraries into this notebook environment directly here in Google Colab. We can do it that way. This exclamation mark means that you use a shell command. This is basically as if I would have typed this into the terminal of this Unix machine. Okay. If you're all confused right now because of this course, just use this in Google Colab, type this command. It means that you install some libraries. Okay. So fine, so good. So we install these libraries in here. Otherwise, you can install this in your Ubuntu distribution on the terminal in the same way, or even run this directly from your Jupyter notebook. If you have a Jupyter notebook environment installed, of course you will probably need sudo rights in order to do this. So you would have to type here basically sudo in front of it and run this in the terminal and give your password if you're not an administrator user. Here in Google Colab it works that easy. Okay. We also need the basemap library. The basemap library is not by default installed in here. We do this like this, and we install this basemap Python library in here, which needs these kind of libraries that we have just installed before here. Okay. So it says, okay, I need to restart my session. Okay, let's do this quickly. So this basically means I need to re-import the pickle file probably. I hope we didn't lose our files. Let's just check this out here. Our files seem to be still here. Let's run this quickly through here. It's very easy. We just rerun the commands. We don't need this one because this is just for visualizing. We import our towns. We transform them to this kind of to these lists. We add the lists to the data frame, and we have our data frame. We're back in business, no? Okay. The libraries have been installed. The base map has been installed. Everything is fine. We can right now start to play around with all of this. Okay. So this is this Python library that I've installed. These are some libraries that this Python library needs in order to work. So far, so good. Let's go back to what do we want to do with this. So we want to use this base map in order to draw a map. So what we will do basically is we will import this this base map tool. So this is called MPL toolkits, and then we have here base map. And from this base map we will import base map. Okay, this is all we need. And in order for this to work, we also need the matplot library, so we will at the same time import matplotlib.pyplot. You already have seen this as PLT, no? So fine, so good. We have our libraries, and right now we can play around with this base map in order to draw a map, and we want to have a map of France, as these are towns in France. How do we do this? So we need to know the latitude and longitude of France. So basically we create like a square or a rectangle around France, which designs us our map in order to plot this map. Okay. So I will call this here my map, and we will do something like base map, and then we can choose a projection. So the projection, we will use the Mercanture projection in order to create our map. You know probably that if you project the world as a sphere basically onto a 2D object, there are different types of maps. We will also go on resolution. I guess this L means low, so this is basically the way this works here. And there's also an area threshold. This basically gives you works all for the in order to draw the map. This is not so important to memorize all this. So if you want to draw a map basically between latitude and longitude, with latitude and longitude coordinates, you can use this kind of data in order to use it. Yeah, so we will start basically with the lower left corner here, and in order to use the lower left corner, so we need the latitude and longitude of the lower left corner. So let's do this here, lower left corner. This is the way it works. And so R, they use R here. And then we need basically longitude, and we say here -5. And we go here, lower left corner, and again our latitude 42. Yeah, so this is where France starts. And then we go to the upper right corner, so URCRN, our longitude, and here we are at 8. Where France basically should end, and upper right corner RN, our latitude 52. Okay. So this is our map. You can adapt this latitude, longitude, corners basically for the map that you want to draw. If you have towns, if you have something, if you want to draw something on a map, this is the way how it works. Okay. So we have our map, and then we want to play around a bit with this. I wrote this here wrong. Projection. I'm sorry for this little spelling mistake. And right now I can use our map and basically say something like draw coastlines. We want to draw certain things on the map, so we want to have basically the map draw LS mask, and we want to have basically the land, we can color the land color. Basically we want to have this in kind of orange tones, and at the same time we want to have the ocean, and the ocean should be sky blue, something like this. Okay, and as we have this even more, we want also to have some topology data on it. So etop, so that we kind of can say mountain ranges on the map, because these mountain ranges have probably an effect on the weather, and as I said, we want to use these clustering tools here in order to cluster these towns according to their weather and discover climate zones, something like this. So in order to understand how we use this DBSCAN algorithm that we have talked so much about it in our last lecture. So far so good. This also kind of introduces you on how to use a map. We see here our little map, very beautiful. We have here the coastlines, we have here the topology, we see this town, basically this whole outline here. Very nice in our browser on the map that we have drawn. And right now we want to have basically the towns and all this stuff here inside. So let's go back to the DBSCAN algorithm. Let's first cluster the towns. As we said, we have basically our towns data frame, just to recover it. And in order to perform the clustering, we want basically just the 4 metadata that we had kind of in this toolkits here, where we had basically temperature, wind, humidity and pressure, but these are the 4 that we're interested for the clustering, and we will export them in order to make them the features that we will use as our clustering. So how do we call the features of an object in scikit-learn most of the time, or in the scikit-learn documentation? So we call them X. So we will use this X here, and we will say wheels, and then there is this kind of location tool. We already talked about this, and we use this basically in order to generate a new data frame. So what I might do here with this double pointer, select everything, and then we want to select the 4 columns that we have. This is basic, how should I say it, basic pandas data frame methodology. So I want to have 4 columns out of it. With this here I could select the rows from which row to which row I want to have this. We have seen this in the first lecture, basically in this introduction to the Python language lecture, in this practical lecture, how to use this. This is just a little recap. So we use the temperature column, we want to have the wind column, the humidity column, and the pressure column. Okay, and we have this here, and we will copy this here over into create a new data frame using this story here. Okay, so fine, so good. When I type X, I see I have a new data frame where the index, of course, we have to cover the index as up here, because then we want to introduce labels to all of them. And we have temperature, wind, humidity and pressure, which are our features of these towns. And what do we see with these features here? Well, they're not in the same ranges. So it would be good maybe if we can rescale them before we perform our clustering and say, okay, we want to have kind of the same scale. You have then always to think how to define our distances, but we use the distances in this kind of rescaled world in order to cluster. So far so good, because this is a bit complicated. We see here that here basically the values, of course, they're in these tens regions. Here the wind speed is in this kind of region, the humidity is in a different region, it's in the hundreds, the pressure is in the thousands. we want to get all of them onto the same scale, so that kind of a distance in pressure corresponds to the same length as a distance in humidity, at least in this kind of data set here. So how do we do this? We will use our standard scaler again. We already have introduced the standard scaler in several prior stories, so we will use from scikit-learn preprocessing. Import the standard scaler, and we have the standard scaler here, and we will use directly, we probably, as we just want to have labels here, we don't need to keep the scaler, so we will transform and fit in one step. So we will call here x scaled, this in our case, and we will call the standard scaler that we have just imported above, and we will use the method which is called fit transform, and we apply this directly on x, so we fit the standard scaler and we perform the transformation in one step, contrary to the prior videos where we kind of keep the standard scaler apart as a fit and then the transformation in order to get new data and in order to classify or use the new data basically in order to perform regression or whatsoever. Here we just want, this is a labeling task, we don't have a training test set split, something like this, we won't have new data in order to classify this, so we just use this in this way. Okay, so fine, so good. We perform this way, we perform this transformation, and this transformation, of course, if we then go to on x scaled and we take, for instance, the first town out here, we see that all the values are kind of in the same ranges, and remember that this kind of gives you a mean of 0 and a standard deviation of 1 for all of these columns. And the nice thing is basically that all these columns are right now in the same data ranges, and that we can give them kind of the same distances from each other, okay? Which is important for our DBSCAN. So as we have done this, we can directly go to our clustering algorithm. So how do we get this here? From scikit-learn cluster, we import. You have seen the DBSCAN algorithm the last time, so of course you could use different clustering methods, but here we will use this DBSCAN that we have talked about in the last lecture. And we have imported the DBSCAN, so how do we use it? I will just call this DB object here, and we will define the DBSCAN, and we can use basically EPS. So EPS is kind of the radius. You remember at the last lecture we have a radius, and we have a minimum number of samples in order to define a density, and then we will find density connected regions in our 4-dimensional temperature, wind, humidity, and pressure space. So spatial distributed data in this case it's not really, because it's of course weather data, but these are 4 dimensions. These 4 dimensions are kind of scaled into the same ranges, and in this new space basically we will search for density connected ensembles in order to find weather zones in France with the weather of these towns, okay? So I will use an epsilon value here of 0.9, as this is 4-dimensional, and basically we have here ranges, let's say between -1 and 1, as they are distributed this way. We have this rescaling factor, so using this rescaling I can intuitively think what are good distances for my clustering algorithm, okay? And we will use basically minimum number of samples. We will say, okay, we want to have 20 samples around one town in order to build a cluster. We have 1,000 data points in the cluster. The epsilon value is basically pretty large, so it should be fine. And we use a metric of the L2 metric. I give you all this because you can play around with these values later on and draw your own maps once you have watched this video and once you have typed all this. Basically, I suggest you play around with this data. Okay, and so in order to run this DBSCAN, we can directly from this DBSCAN, of course, run the fit function on it. So this works exactly like any classifier, any regressor. Just here we don't have any labels, we generate the labels. Okay, that's basically everything that you have to know. So we fit basically this X scaled. We don't need a number of clusters. Different clustering algorithms might ask for a number of clusters that you want to find. I refer you to the scikit-learn documentation in order to look into these clustering algorithms. There are different clustering algorithms, of course. Here we, as I said, we go into the DBSCAN. We have the radius, the minimum number of samples. This gives us a density. Yeah, so number of samples divided by volume. So this is a hypersphere. In this case, an Euclidean hypersphere, so a sphere in 4 dimensions with the radius 0.9. Metric, we use the L2 norm, so the Euclidean distance basically with this minimum number of samples here, this gives us a density. Okay, so density points in volume, minimum number of points in the volume, and we look basically for a density connected cloud which satisfies this density argument here, and we directly apply this with here, it's called a fit function, so that they basically in scikit-learn always use the same terminology, so that you run this DBSCAN using this fit method. Okay, so fine, so good. We run this here directly with this DBSCAN argument. If I type here DB, and then I can basically, then we get here out labels, no? And this DB labels, this is basically what we want. This is basically the Y that we normally supply. So here we get the Y out because we have a clustering algorithm. When we look at these labels, we see we have these -1s here. So these -1s are basically, if you remember, the white dots in these graphics that you had in the last lecture. These are the outliers, so which are not in any cluster. And then we have the clusters, so they start to number them at 0, yeah. And from 0 we go up here. We see here we have 3, 4, 1. These different towns clustered together. Okay, so I want just to check, let's make some kind of checks here, and work a bit around with this. And we also want to color this according to each cluster on the map. So I could just kind of add this to this data frame right now. I don't want to do this, but I want to make basically a quick check. If I take these labels, if I type here max behind it, I will see how many clusters do we have, and we have basically 4 clusters. And then I will go on a bit playing around with these clusters, what we can do. So I need the NumPy library, and we basically want to attribute a color to each of these clusters. Yeah. So how do we do this? So I will call these colors, and then I will use this massplot library that we have basically imported. And this massplot library, it has a color map functionality. So here you can search for different color maps. I will use the jet color map, and then you can basically use here in NumPy, we have this linear space convergent, and we go here from 0 to 1. So basically I want, you see the labels here, they go from -1 of course to 4, so the maximum is 4, so we have 5 clusters, and -1 are the one which are not basically in, which are the outliers. Yeah. So I will do this very easy here. I will call this here from, so I make this kind of transformation here for all these labels. Okay, +1 in order to be on the safe side. So what I basically do is I generate a linear space transform for each between, so basically I map the space from 0 to 5 into this to 0 to 1. This is everything this does, yeah? And this generates me this color map here. Okay, so fine, so good. So then I also want to count how many -1s do I have, so how many outliers, how many towns do not fit into a cluster. We have seen we had several -1s here. We also want to count them to make sure that our clustering makes kind of sense, just to see what's going on here. Okay, so far so good. Let's perform our loop here. Let's attribute a color to each of our clusters. So in range. So I programmed this here so that this basically for a different clustering works, so that basically once we have done this, we can just change the values and discover different maps if you would like to do this. If you do this at home, you can just then use this functionality and play around with these epsilon values and minimum sample values. You also can replace the metric from L2 to L1. I suggest you do this and play around with it at home, kind of as a home exercise to this course. Okay. Okay, DB labels underscore. These labels have this underscore here. When you use this functionality in order to memorize a bit the syntax. Okay. Okay, so if we find a label which is number 1, we want to basically increase the count here. Okay, so if this is -1, we want to say we want to do the following, because we want to have at the same time, basically we want to attribute a color for each of our towns, yeah, and of course we want to color them according to the clustering that we have in the DBSCAN. So I added here this color list, yeah, and if this is basically -1, I didn't include this in this linear space, yeah, because this goes from 0 to 1 and it maps basically from 0 to 1, basically from 0 to 5. Yeah. So what do I need to do here? So I need to create the gray color. So I want to have basically that this one here has the gray color, and the gray color basically works with these triplets here. So red, green, blue, 0.4. So if all the values are same, this is basically a gray color. Yeah. You can try this out. It goes from black to white. If you change all 3 colors at the same time, this stays gray. Okay, very intuitive. And this is not a cluster, so at the same time I say, okay, let's increase these not clusters. Here this is called not clusters, of course, otherwise this does not work, by +1. Okay, and so I count my clusters. In the other case, if this is a cluster, so if this is not an outlier like this, as we have this -1 here, then we also need a color, but then we can of course use the jet, that what we have defined here, so this functionality here with this linear space, and we just basically say, okay, append, and we can basically just say here colors using the DB labels _I, and this works. So I can basically call these colors here and get the right color for the label out here with this linear space color map transform. Okay, looks a bit complicated, isn't so much complicated. So basically it looks up the color here with this kind of list or like object here, and returns the right color, and we append this color into our color story here. Okay, I hope this is half clear to everybody at least. Okay, this is how this works. Also look at the syntax. This is basically how we get the colors. We use this linear space, we use these labels here, we use the jet. We could use here something else, you have to look it up in this get cmap, functionality, basically color maps in the matplotlib library. You find this in the documentation online, of course, of the matplotlib library, what kind of color maps they have. Yeah, okay. This chat is very nice. It works very nice with our map, and we can add this grayscale here again in order to map this out here. Okay, so fine, so good. We run this in order to generate this. And we have done this, and then we can see how many towns have not been clustered. And we have, this is 161, just to memorize. How many towns do we have? 889. So of these 889, 161 are outliers. Okay, this is still fine. This doesn't matter. They don't fit kind of into a common climate with the other towns. This is kind of expected. We want to use this, and this basically, that's the way it works. Okay. Okay, right now we have to draw this on the map. So we need XY on our map, and we use this with this map that we kind of have generated, and we can use this map here, and we can see here XY. Basically, we want to have our towns, and our towns, they have this long tag column that we can use. I will use this with 2 numpy in order not to run into issues, to have them basically in the right shape. That's the way it works. Yeah. Latitude. Okay. Again, 2 numpy. Okay. So this gives me these x and y coordinates on my map mapped from the latitude and longitude functionality. Okay. We want to draw the map. We know how we do this, so we want to have again, we have already shown this, so we want to have the coastlines and all the kind of stuff. What I didn't do beforehand is we want to see friends, so we want to have draw countries, so that we basically see the border to Germany and things like this. It's a bit more nicer to do this, no? And then we have our map, and we want to have, of course, these the oceans in blue. So we use this with the orange blue story here. So we have here land color. We remember this was orange, and ocean color. I should have just copy pasted, but right now I'm already typing it. Sky blue. Okay, and we want to have, of course, the topology in order to see on our map where there is a mountain knot, and we have these kind of towns here. This is all very nice. We want, of course, to draw the towns, and we want to use this with the scalar, and so this works a bit like the matplotlib, so we can use this scatter story here. And we need an XY coordinate on our scatter, which we got from the map and from this latitude longitude story up here, which is very nice. And we can say then C equals C. This is basically the color, and the color should be our color array that we have generated with this code up here. Okay, so remember, outliers are gray, the other clusters, they get basically color from this jet color map up here. Okay. Let's watch our map, and there was something here went wrong. Input must be a scalar. Why does this work? Okay, here to numpy, this is not a scalar. I'm sorry for this little spelling mistake. I forgot here these brackets. And we see, big surprise, our map, and this is very nice. So we perform this DBSCAN clustering, and we see basically that all towns here in this upper part basically fall in this blue cluster here, and we can detect basically that by this, let's say, mountain range here, by this Massif Central here in France, is this here, and by this extended mountain elevation here, so where the elevation here goes up, that basically a second climate zones forms, which kind of is the same as these Mediterranean towns here. And we see that we have here basically the dark blue side and the light blue side of things, and in between we kind of have these orange stories here, but these orange stories, they more correspond probability series here, the town of Bordeaux. We have here the city of Paris, which forms with some little other towns its own cluster. So we found these different climate zones here, and this here is kind of, let's say, the mountain ranges, which have of course their own climate here in the mountains. And we can basically discover how we can use this DBSCAN algorithm in order to discover basically climate zones here in this on this map, as we have done it right now. Okay, so of course I ask you, you can play around with these values here, then you will get out different maps than the one that we have done here. What you should basically memorize from this course is how to use this DBSCAN story. So basically you have a data set which has some labels, these are basically, which has some features, so these are basically the features. The data set has no labels, no targets, like in the regression or classification story, but you want to generate labels to basically to these features, and we find here with these radius and sample values that we get basically 5 different objects out of it. So 5 clusters, if you wanted. We get these 5 different objects, and they correspond basically to these 5 climate zones that we discover here in France using this clustering algorithm. Okay, so the clustering algorithm was DBSCAN algorithm. The DBSCAN algorithm was highlighted in my prior video from this course here. That's everything for this video. I hope this basically gave you a pretty practical introduction in how you can use DBSCAN in order to find clusters in your dataset. Okay, so far so good. We have learned a bit about the scikit-learn library. We also have shown you how to draw basically towns on a map, how to draw maps. Not so important to know. This is not so much about machine learning, this is more about visualization, but in order to have a bit more fun in this course we did this and use this kind of DBSCAN algorithm in order to find out our clusters. Okay, thanks so much. Thank you for watching this other video. I will stop here. Goodbye.